Hello everybody! In a previous video, we learned about a new vector operation called a dot product. In this video, we're going to learn about another vector operation. This one is called the cross product. And it has a lot to do with perpendicular vectors. Now, we learned that the dot product can be used to check if two given vectors, say v and w, are perpendicular. Because if the vectors v and w are perpendicular, the angle between them would be 90 degrees, and the cosine of 90 degrees is 0. Now, previously, we learned how to calculate the cosine of the angle between two vectors using the dot product, and when the cosine is 0, that also implies that the dot product of those two vectors is 0. So given two vectors, you can easily check if they're perpendicular. But what if you turn this question around? Let's say you just start with a vector v. How could you find a vector that's guaranteed to be perpendicular? In two dimensions, it's not too hard to calculate as follows. Let's say you have a vector v that's equal to ab. Now you can calculate the slope of this vector, the rise over the run, or the change in y over the change in x. Either way you say it, the slope of the vector is b over a. And something you might have learned a while ago in an algebra class, but if you didn't, or if you forgot, now you know, perpendicular lines in two dimensions have negative reciprocal slopes to each other. So if the slope of the vector v is b over a, then the slope of a perpendicular vector, say w, would be equal to negative a over b. So we need to produce a vector which has the slope of negative a over b. Well, one such vector w would be b, comma, negative a. Or, it doesn't matter where you put the negative sign, you could use the vector negative b, comma, a. Or, as it turns out, you could use any multiple of these vectors. You could use any constant c times the vector negative b, comma, a. Why are there so many right answers? Well, there's lots of perpendicular vectors to any given vector v. So if you're looking for a vector perpendicular to v, this red vector here might be the vector b negative a. This orange vector, pointing in the opposite direction, but still perpendicular, would be negative b, a. And you could multiply either of these vectors by any constant, and you'd still get vectors which are perpendicular to v. They'd just be different lengths. So there's lots of right answers. Now let's think about two dimensions. Or first let's do an example, and then we'll talk about three dimensions. So a two-dimensional example. Let's say the vector v is 2, 5. A perpendicular vector will have negative reciprocal slope. So you can think of this almost as the negative reciprocal vector. Take the components and switch them and make one of them negative. So starting with the vector 2, 5, a perpendicular vector would be 5, negative 2. And if you want to double check that these two vectors are perpendicular, you could calculate their dot product. And the dot product of v and w is 2 times 5 plus 5 times negative 2. That's 10 minus 10, which is 0. So that checks out. And in general, to see that the formula we talked about on the previous page always works, we can check the most general case algebraically. If you have a vector v, it's equal to a, comma, b, and another vector w, that's equal to c times b, and negative c times a, you can calculate the dot product of these two vectors. v dot w will be equal to, the first times the first component, so a times c times b, plus the product of the second components, so b times negative c times a. So that'll be acb minus bca. Those are really the same numbers with their factors rearranged, so that gives you 0. Right, so for any values of a and b, you can use any value of c, and you get perpendicular vectors. Right, 2 dimensions is not too hard. In 3 dimensions, it is a bit trickier, but it is manageable. The first thing we should talk about is how many correct answers could there be? So I'm going to try to draw something in 3 dimensions again. So once again, let's say we have 3-dimensional space and an x, y, z axis. And as before, I like to think of the axes as the back edges of a cube. Right? So x, y, and z are all perpendicular to each other. And let's say you have a vector that's pointing out along the y direction. So let's say v is pointing along the y direction. Turns out, again, there's lots of vectors perpendicular to v, but in this case you get an entire plane of vectors perpendicular to v. The collection of all these perpendicular vectors forms a flat surface. Again, it's kind of hard to visualize 3-dimensional pictures, but you could imagine v as like the y-axis, and then all these vectors would be any vector lying in the xz plane, which would be the left side of this cube here. Any vector completely contained in that side would be perpendicular to v. And so that's a lot of correct answers. The case we'll be more commonly interested in is a set of vectors which is perpendicular to 2 different vectors at the same time. And so imagine in 3-dimensional space, you have a vector v pointing out and a vector w pointing in a different direction. And we're interested in the set of vectors perpendicular to both v and w. Well, in that case, the set of vectors actually forms a line. And it's more similar to the 2-dimensional case, so we'll usually work with this set of conditions, finding the set of vectors perpendicular to 2 given vectors. In this question, it really only makes sense in 3 dimensions, right? If you have 2 vectors in 2-dimensional space, it's going to be hard to find a vector perpendicular to both. But in 3 dimensions, this makes total sense. Right? Like for example, if you wanted to find any vector perpendicular to both the y-axis and the x-axis, those vectors would all run along the z-axis. So we kind of know qualitatively what we think the answer is going to be like, but we still need an algebraic formula to calculate this. And so that formula is called the cross product. You can think of it as an operation or a formula for calculating a normal vector, which is also a perpendicular vector is also sometimes called a normal vector. That's why I'm using the letter n. You can calculate this perpendicular vector n from 2 other vectors v and w. And we'll usually write that using the notation n, vector n, is equal to a vector v cross the vector w. Now, in order to more easily remember this formula, we'll often use something called determinant notation. And this is kind of a preview of a topic we're going to see a lot when we start talking about matrix algebra in the next third of the course. So to remember this formula, the cross product of 2 vectors v and w, let's say that the vector v has components v1, v2, v3, and the vector w has components w1, w2, w3. So first, I'll arrange these values in a grid. Along the top row, I'm going to write the standard basis vectors I, j, k for 3-dimensional space. Right? We mentioned these when we first started talking about vectors in 3D. These are the unit vectors which point along the x, y, and z axes. So I is the vector 1, 0, 0, j is the vector 0, 1, 0, k is the vector 0, 0, 1. Right, so along the top row, write I, j, and k. Along the next row, write the components of v. And along the last row, write the components of w. Now, what we're going to do is we're going to extract little 2 by 2 sets of numbers, and we're going to put them, again, in blocks like this. A block of numbers is also called a matrix. This we'll spend a lot of time talking about in the future. The way you determine which numbers to use in front of I, j, and k, so for instance, the numbers we use when calculating the I part of the cross product, the first component of the cross product, ignore the values in the column of I, and the remaining values are going to be used to calculate that number. Similarly, to calculate the j part of this vector, the second component, the numbers we're going to use ignore the numbers in the column containing j. So ignore these. You're left with v1, v3, w1, and w3. So those numbers we'll use for the second component. For the third component, the k part of the cross product, again, ignore the values in the column with k. And the numbers that are left, v1, v2, w1, w2, we're going to use those to calculate the third component. Now, what do each of these blocks of numbers mean? Well, it's something called a determinant. In general, if you have a 2x2 block of numbers written like so, the determinant of this is calculated as a times d minus c times b. And so each of these 2x2 blocks of numbers we're going to replace with this expression. And the way I like to think about it is, imagine kind of this swooping pattern right here. A times D minus C times B. And if I was in class right now, I would swoop my finger around every time I calculate one of these determinants. So this first block of numbers, right, that's the I coefficient there, the first part. That's V2 times W3 minus W2 times V3. The j part is going to be v1 times w3 minus w1 times v3. You see that here. Finally, the k part is v1 times w2 minus w1 times v2. That's this part right here. The other thing to pay close attention to is that the signs alternate in front of I, j, and k, for a very technical and not important to us reason. So I and k, those parts are just normal positive numbers. We're going to flip the sign in front of the second component. So there's a negative sign right here. So be sure to distribute that through. Now, I wrote this as something times I minus something times j plus something times k. But remember, I is the vector 1, 0, 0. J is the vector 0, 1, 0. K is the vector 0, 0, 1. So you can actually multiply this through, and you'll be left with this vector. And that is the cross product. Let's try some examples. All right, so let's say I want to find the cross product of these vectors. V is the vector 2, 3, 4, and W is the vector 5, 1, 6. Right, to calculate that, to calculate the normal or perpendicular vector n, it's equal to V cross W. I'll start off by drawing this 3x3 grid. Top row is always I, j, k. Second row is the numbers of V, 2, 3, 4. And the last row are the entries of W, 5, 1, 6. And then I'm going to break this 3x3 grid into 3 2x2 grids to find out the coefficient of I. Right? Ignore the numbers in the I column and take the remaining numbers, put them in a grid. For the coefficient of j, the second component, ignore the numbers in the column j, take the remaining numbers, put them in a grid. For the coefficient of k, ignore those numbers, take the remaining numbers and put them in a grid. And then we're going to calculate the determinant of each of these blocks of numbers, each of these matrices. So in front of I, we'll have 3 times 6 minus 1 times 4. 3 times 6 minus 1 times 4. For the coefficient of j, we'll have negative 2 times 6 minus 5 times 4. 2 times 6 minus 5 times 4. Finally, the coefficient of k, we'll have 2 times 1 minus 5 times 3. 2 times 1 minus 5 times 3. A nice catchy little rhythm there. And then we just do some arithmetic. So this first part will be 18 minus 4, or 14. The second component will be negative 12 minus 20. See, 12 minus 20 is negative 8. So negative 8. so that's positive 8. Finally, we have 2 minus 15. That gives us negative 13. So this vector, turns out, is perpendicular to the two original vectors, v and w. So, in case you want to check your work, which you should always want to do, to check that, we know that two vectors are perpendicular if their dot product is 0. So what we can do to check is calculate some dot products. The vector n dot with the vector v should give us 0. So we take n dot with v, so I have 14 times 2, which is 28, plus 8 times 3, it's 24, minus 13 times 4, it's minus 52. And if you add those up, 28 plus 24 minus 52 is 0. That one checks out. Just to be doubly sure, we can do the vector dot with w. So 14 times 5 is 90. 8 times 1 is 8. Negative 13 times 6 is negative 98. Sure enough, combine those numbers, and you get 0. So the cross product works as promised. We should do one more example. So let's say we have the vector v, which is negative 3, 4, 7, and the vector w is 1, 2, 5. To find the normal vector, the cross product, v cross w, we'll create this grid. Top row is I, j, k. The next row is the components of v, negative 3, 4, and 7. The last row is the components of w, 1, 2, and 5. We'll extract our 2 by 2 grids, right? The coefficient of I, ignore column I, 4, 7, 2, and 5. For the coefficient of j, ignore column j here. We have negative 3, 7, 1, and 5. For the coefficient of k, ignore column k here. Left with negative 3, 4, 1, and 2. All right, time to do some determinants. For the coefficient of I, 4 times 5 minus 2 times 7. That's 20 minus 14. That gives us 6. Then we have negative 3 times 5 minus 1 times 7. Let's see, that's negative 15 minus 7. That's negative 22 in the parentheses. Don't forget this negative sign. Negative 22 is positive 22. Finally, negative 3 times 2 minus 1 times 4. Negative 3 times 2 minus 1 times 4, that's negative 10. That's the last part of our vector. All right, and now to check this, I have n dot v. So I'll take this vector, dot it with v, and I should get 0. 6 times negative 3 is negative 18. 22 times 4 is positive 88. And negative 10 times 7 is negative 70. If we add those up, we get 0. Then n times w, see 6, 22, and negative 10. Dot with 1, 2, and 5. 6 times 1 is 6. 22 times 2 is 44. Negative 10 times 5 is negative 50. Combine those up, and you get 0. Hey, math works. That's comforting. As a funny thing, too, when I was creating the slides for this lecture, I actually made a mistake in the calculation. I actually forgot one of the negative signs here. It's a good thing I checked the work, because when I found that the dot product didn't equal to 0, I was able to go back and pay closer attention, and I realized I had dropped a negative sign. So it's always good to check your work, whether you're a student or a professor. Now, just a couple of notes, just for fun, about the cross product. Unlike the dot product, right, the cross product involves some subtraction. So the cross product is not a commutative operation. V cross W is not the same. It's not equal to W cross V. Right? In both cases, you will get a perpendicular vector, but they will be different perpendicular vectors. In particular, the cross product has a property which is sometimes called anti-commutative. V cross W is equal to the negative of W cross V. In other words, if you switch the order of V and W, every part of your answer gets negated. Right? And that just means it's giving you a perpendicular vector, but one that points in the opposite direction along that line. Now, if for some reason you really want to determine which one of these directions that you're getting when you calculate the cross product, there's a way to do it using something called the right-hand rule. The idea is if you take your right hand and you cross your fingers in the direction from V to W, then your thumb will point in the direction of the cross product. It's something called the right-hand rule. We won't use it too often, but you might see it in, for instance, a physics class if you use this operation. Also, there's a formula for the cross product that helps you calculate the sine of an angle between the two vectors. Cross product and dot product are really very closely related. Remember how the dot product lets us calculate the cosine of the angle between the vectors? In this case, we have the following formula. The length of the cross product of V and W is equal to the length of V times the length of W times the absolute value of the sine. So it's not exactly analogous to the dot product formula, because in this case it uses the length of the cross product rather than just the cross product itself, and it uses the absolute value of the trig function rather than just the trig function. But if you rearrange this equation, you'll see something very similar to the cosine formula we get when we use the dot product. Right, so these two are very similar. I don't think we'll ever actually use this fact in the class, but I think it's kind of cool that there's this close relationship between these two formulas. But the primary purpose of the cross product formula is to calculate a perpendicular vector to two given vectors. And as we'll see, this is going to help us a lot when we do calculations involving lines and planes in a future video. But that's it for this video. It's an introduction to another new operation on vectors, which we'll see a lot of in the future. Thanks for watching.